All right, so let's get started. Hi, everyone. So it is our honor and pleasure to have Daniel Lecker from Columbia as our SNAPP speaker today. So Daniel is an associate professor in the Department of IUR at Columbia University. He was an SF postdoctoral fellow in the Division of Applied Math at Brown University. And prior to that, he received his PhD from Princeton and his bachelor from Carnegie Mellon. So he's the recipient of several awards, including the Alfred Sloan Fellowship, an NSF Career Award, and a SEAC FME Earlier Career Prize. Daniel's primary research areas are mean field games and interacting particle systems, which form the mathematical foundation for a wide range of models of large-scale interactions arising in physics, engineering, economics, and finance. So today, Daniel will be presenting to us on projected Langevin dynamics and gradient flows for optimal transport and variational inference. So Daniel, the floor is yours. Thank you so much for accepting our invitation. You have around until 9:30.
Okay, thank you very much for the generous introduction and the invitation. I'm happy to see this seminar alive and well that kept us going in the early COVID days. Happy to follow over the years, and I'm happy to share my work with you all today. As a first disclaimer, I'm a bit out of practice with the Zoom setup, so please let me know if the audio gets weird or cuts out at any point. And more generally, feel free to interrupt me along the way with questions. I kind of enjoy the interruptions, especially in the online setting here. So the work I want to talk about today is based on one paper mainly, but a bit, as time permits, of a second paper as well that came out on arXiv a bit over a year ago. And the papers are really about fascinating new stochastic processes in continuous time that come up in connection with gradient flows. But the more accessible and I think perhaps more exciting story is that this connects naturally with topics in the theory of sampling. So it's from that perspective of sampling that I want to tell the story here today, although the papers won't say much about this direction. This is more kind of an ongoing maybe on the horizon ambition for where this line of work is going. So let me first say that this is based on joint work with Giovanni, Conforti, and Soumik. So before I get into the new stuff here, which will be kind of new sampling type methods related to two application areas, mainly optimal transport and a bit also variational inference as time permits. Let me start by reviewing a fairly classical, well-known picture related to the Langevin dynamics in connection with sampling. So a very common and basic problem in applied probability is the following one. Given a probability density, how do we generate samples from it? Now, what makes this problem often challenging is that the dimension may be fairly high. This may be a high-dimensional distribution, and maybe also the density is only given to us in unnormalized form. So here rho star is what I'm calling some probability density, which is given to us as just being proportional to e to the minus f over epsilon. F is some given function, and there's some hidden constant of proportionality here that might be very difficult to compute on paper or on a computer, let's say. Okay, so this kind of very basic problem has been around for quite a while, and there are many different methods for how you would generate samples of this form. If you're in low enough dimension, you can often do numerical integration, but in high dimension, Monte Carlo methods are generally favorable. And the very popular one comes in connection with the famous Langevin dynamics or overdamped Langevin dynamics, where this probability density comes up as the invariant measure of a certain Markov process. And when you're in a situation like this, the idea is to try to simulate the Markov process for a long time, initialize it wherever you want, simulate for a long time, and it forgets the initial position and converges to the density that you're trying to sample from. So the Langevin dynamics are given by the stochastic differential equation here, where the function f from the density we're trying to sample from comes into the gradient. Its gradient shows up in the drift, and we add a bit of Brownian motion the epsilon noise level corresponding to this epsilon parameter in the density. Okay, so this is a very well-studied stochastic process in a ton of different applications. The way to think about this is that if you ignore the noise term, you just have a standard gradient descent in Euclidean space, which will tend to, push you toward a local minimizer of the function f. So if this is your function f, then of course this gradient flow just pushes you towards a local minimizer. Now, of course, the gradient descent itself, if f is non-convex, can get stuck at a local minimizer like this one, depending on where you initialize things, and never make it to the true global minimum over here. Adding any little bit amount of noise will free you from these local minima traps, at least if you run time for long enough. The idea being that eventually the Brownian fluctuations will kick you over the hill, and then the gradient flow will push you towards the true minimizer. So this is a kind of natural connection here then between a first glimpse of the connections between sampling and optimization. As a kind of way of relaxing the optimization problem, you might instead kind of add this noise parameter, and this leads to the idea of simulated annealing, which I won't talk about too much, but in which you let the epsilon parameter depend on time. And there's a beautiful and rich theory around the behavior of these dynamics with or without this time-dependent noise parameter. And I'm not going to spend a whole lot of time on this except as kind of background and setting up an analogy for the new stuff I'm going to talk about a bit later on. The essential point for now is that if we fix the noise level and we run this SDE, the stochastic differential equation, for long enough, the distribution of the solution will converge to this density rho star that we want to, let's say, sample from. Now, of course, this is all very nice in theory, but in practice, to implement this, we need to discretize this continuous time process. And this is normally done using an Euler scheme. At least the most basic way to do this is to just, discretize the time step in an Euler scheme. And you have, say, an h times the gradient of the drift, and you just simulate a standard normal at each time step to generate the Brownian motion for you. And if you kind of run this process for long enough, if h is small, the time step is small, then you're not too far from the continuous time process, and you hope that this will give you an approximate sample from your rho star density. Now, this passage from the continuous time to discrete time is kind of full of subtleties and challenges in terms of really doing a precise, sharp analysis of the convergence rates and the dependencies on different parameters, the step size, the noise level, how the dimension appears, for instance. And this is a rich area of research still to this day. So there are two textbook references I'm putting at the bottom here, and I'm especially fond of this really nice free monograph in progress by Sinho Chui on his website that really gets into all the details of convergence analysis for what you might call Langevin Monte Carlo algorithm, which is the time discretization of this SDE, and variants of it used for the purposes of sampling from this density rho star. Okay, so again, this comes up a lot in high dimensional contexts because, okay, this suffers like everything does from the curse of dimensionality, but Langevin Monte Carlo doesn't suffer too badly, it seems. The scaling with the dimension is linear or square root sometimes, depending on the details of what you're doing. And because of this, it's very popular in areas like molecular dynamics, where dimension has to be really huge typically, and also in Bayesian statistics. So I want to say a bit more about this process before I move on to the new stuff. One is to kind of zoom in a bit more on the connection with optimization. So I mentioned here the other way you can express this evolution of the distribution of your process is through a partial differential equation, as is kind of standard when you're dealing with SDEs. the density of xt will evolve according to this Fokker-Planck equation. I'll refer back to that a bit later on, but for now, that's not so essential. There's another way you can kind of characterize this density, this invariant measure rho star that our SDE is converging to. And this is as the optimizer, the unique optimizer in a certain minimization problem or variational problem over the space of probability measures. And this optimization problem takes this form. There are two terms here. You could write it in this way with two terms. The first term is what you might call the potential energy. And the second term you might call the internal energy if you're a physicist, or maybe the entropy is the more recognizable term here. The second term is just the differential entropy. And the first term is the expectation of your function f with respect to the distribution rho that you're choosing. Okay, and if you get to optimize the sum of these two quantities over all possible choices of probability densities, the unique optimizer will be your invariant measure rho star. Now, another way you can package this, if you group these terms together, this is exactly, I think I forgot the normalizing constant over here somewhere. But if you package these two terms together, this exactly gives you the relative entropy, also known as Kullback-Leibler divergence, between the rho that you're choosing versus the rho star, the actual optimizer. And the well-known property of this relative entropy functional is that if you vary the first parameter, you only get 0 precisely when rho equals rho star. So this kind of optimization perspective gives you another point of view, another way to describe this probability distribution rho star. And this kind of plays a key role in this beautiful connection with geometry and optimal transport that emerged 25 years ago or so. Which I don't want to assume that you're familiar with or certainly not experts in. So I'm only going to flirt with this perspective a little bit throughout the talk without trying to get into really the details of explaining this notion of Wasserstein geometry or autocalculus. But to paint a kind of sketchy picture here, the idea is essentially that if you use the quadratic Wasserstein distance, which is kind of famous in the world of optimal transports, to equip the space of probability measures with a certain distance, then there's a natural geometry associated with this space that's kind of that kind of makes the space of probability measures informally into a Riemannian manifold. And once you're in the context of a Riemannian manifold, you can talk about gradient flows. And in this geometry, this Fokker-Planck equation is precisely describing the flow of steepest descent for this relative entropy functional. So this gradient flow perspective has been very influential in recent years in the sampling literature, in part because it kind of gives you a justification that this Langevin approach is in some sense canonical. It's natural in some sense. It's really doing the steepest descent for this entropy functional, at least subject to a very natural notion of distance between probability measures. But the geometric perspective is actually very useful as well for the design and analysis of algorithms, of sampling algorithms, because once you view this flow of distributions as really a form of gradient descent, you can go over to your Euclidean space kind of standard gradient flow toolbox, all the tools that have been developed for optimization in Euclidean space and connected with gradient descent. And you can start to port these things over to this world of sampling by trying to do similar analyses for this gradient flow in the space of probability measures. And so again, this monograph of Chui that I mentioned on the previous slide is a great reference for these kinds of ideas. And this really has been a kind of driving force behind a bunch of new algorithms that have been proposed as well, kind of adapting ideas from Euclidean optimization theory into this, sampling this space of probability measures, essentially. And so it's kind of in this spirit that this work was born that I'm going to talk about. But again, this geometric perspective will sort of float behind the scenes, and we won't go into technical detail about this. So the main focus of my talk here will be about certain related kind of sampling questions, but where the distribution that you want to sample from is described only kind of implicitly as an optimizer of some sort of variational problem like this one we just saw on the previous slide, but where there's some constraint set, let's say. There's some subset of probability distributions that you're allowed to optimize over. So I'll give you a few different examples that fit in this form, but the kind of general form here that they all fit in is this one, where we're minimizing the same relative entropy functional with some given reference measure rho star, but there's some set M telling us which measures we're allowed to choose rho from in this optimization problem, in this variation problem. So again, I'll give you a few examples going forward, and of course, there are some problems that come up where this relative entropy or KL divergence is changed to a different function. Okay, and there's a kind of parallel thing you could do in that context, but to keep things more concrete, I'm going to stick with this relative entropy throughout this talk here. So when you're encountering a problem like this, if you're sold on the geometric perspective, then the kind of natural thing to do here is to view whatever your constraint set of probability measures is, view that as some kind of submanifold of this Wasserstein space, this kind of informally Riemannian manifold of probability measures. And a submanifold kind of inherits its own geometry from the larger space. And you can try to understand this submanifold geometry and use it to derive a gradient flow equation for the same functional, but now in this submanifold. And this is tricky to do in most cases, to really identify a nice form for this gradient flow, but this has been done in certain contexts, and our work is a kind of new example of this. So the earliest examples I know of are, completely unrelated to the theory of sampling, are coming up in kind of more physics-motivated work, especially the big one being this paper of Carlin and Gangbo from about 20 years ago, where they're trying to construct solutions of Fokker-Planck and Boltzmann type equations with certain quantities that are constrained or conserved over time. So the particular constraint set M that they're looking at is this one, where you have a fixed first and second moment for your distribution, essentially. And they want to kind of identify some evolution of probability densities that meets these constraints at all times. So that's a first example. A second class of examples is more recent and comes up in connection with variational inference, which is a big topic in Bayesian statistics, which I'm very new to. There are two very nice references, kind of survey and textbook references listed here. The general story, as I understand it, of variational inference is that in kind of Bayesian statistics problems, you often end up with your rho star is some complicated posterior distribution in high dimension, and maybe for whatever reason, this distribution that's handed to you is very hard to work with, perhaps because of the high dimension, perhaps you don't know the normalization constant. For whatever reason, this is hard to work with, and you would like to instead approximate it by a distribution from a nicer class. And so this problem set up here, this variational problem, is exactly kind of the starting point of this idea of variational inference. You pick your nice class of measures that you'd prefer to work with and somehow find the closest one to your true distribution from that class. So the two kind of most popular classes to work with here, as far as I understand it, the first naturally is the class of Gaussian distributions. And there's a very nice paper from a couple of years ago that kind of took this geometric perspective on this problem and said, okay, to identify algorithmically the best Gaussian measure to work with here for this problem, we're going to figure out really, like, intrinsically what would be the gradient flow for relative entropy in this submanifold of Gaussian measures, which has a very nice, fairly explicit structure. Okay, and this gradient flow perspective leads them to a very systematic, like principled construction of algorithms for this purpose. Now, the second most popular class, as far as I know it, in this variational inference world is what's called the mean field class, where this set M, this constraint set, is just product measures. So instead of looking at any old measure on Rn, you look at probability measures under which the coordinates are independent. So the densities factorize. Of course, independence is a very nice kind of structure to be able to work with. It somehow frees you from the curse of dimension a little bit because you can work with these lower dimensional marginals and sort of paste them together then. Now, I think in practice, most of the time, they're really using a kind of parametric subfamily of the space of product measures, where sort of each marginal is chosen from some parametric family here that can be optimized over more easily. I'm seeing a question in the chat. The space of measures is not a vector space, and M is not a subspace. How is this usually dealt with during optimization with projection of some sort? Yeah, so as we go on, I'll kind of explain, to address this question, I'll explain a bit of where, why I'm using the term projection in the title. But you're absolutely right that the space of probability measures and the subset M will not be a vector space, but they can be thought of in a useful way as Riemannian manifolds. So they're not flat spaces by any means, but the kind of geometric intuition comes from, identifying and getting to know, again, a non-flat geometry on these sets. But again, that'll lurk mostly behind the scenes here for intuitive purposes. So I hope that addressed the question to some extent. So as time permits, I'll give some glimpses of this mean field variational inference gradient flow, if you like, at the very end of the talk. So in one of the two papers of mine from last year, I identified the kind of gradient flow dynamics. I didn't implement it in any way algorithmically, though I know of a group or two that's working on this at the moment. The one I want to focus on for this talk is a problem where this constraint set is given as the set of couplings of some given marginal distributions. And this is exactly the kind of setup that comes up in the theory of optimal transport. And when you're dealing with this relative entropy functional as your optimization criterion, then this puts you in the world of what's called entropic optimal transport, which I'll introduce in the next few slides. And two very good references on this from recent years are this computational optimal transport book from Perret and Couturi. And very recently, there's a beautiful set of lecture notes called Statistical Optimal Transport from three authors here. So this kind of problem is a bit more challenging than some of these others. To very briefly mention some of the geometric view, this space is not, it turns out, geodesically convex, whereas some of the others are. The variational inference examples are geodesically convex. This first example actually was not from the previous slide. So this is kind of the more challenging case than the other paper that I might present a bit at the end. So this leads to some interesting new subtleties. So this is in part why I'm choosing to focus on this example. So for the rest of this talk, I want to focus, on this case, but this is really, I insist, part of kind of a broader principle that's behind the scenes here, which is that there really is sort of a principled way to build sampling algorithms for problems of this form, where you want to access some distribution that's characterized through a variational problem like this, particularly where there's a constraint set coming. Okay, so with that said, let me turn to the real focus of this talk here, which is this entropic optimal transport problem. So I don't need much of anything deep from the world of optimal transport, but I want to take a couple of slides to introduce the basic problem setup and explain where it comes from. So forgive me, I'm sure many of you know the basics of optimal transport already, but to get us on the same page, let me say a few words here. So an optimal transport problem has three ingredients, let's say. Two of them are marginal distributions. So I'm calling them mu and nu, and each is given by some nice probability density, e to the minus u of x and e to the minus v of y for these two marginals. And now we're also, so these will take place in dimension D. So this dimension D is fixed throughout for now. And we're also given some cost function of two variables, so two elements of RD. And the optimal transport problem asks us to minimize the expectation of this cost function over all choices of probability measures pi, which couple these two marginal distributions. Now, the history of this optimal transport problem and where the name comes from is that you think of mass as being moved from a point x to a point y. The coupling tells us kind of how to do that. So the initial x mass distribution is according to mu, and the target distribution nu is where you want to send this mass from mu. And this pi tells us for a given point here, x, what's kind of the distribution of points that I'm going to send it to for the target distribution. And a particularly important class of couplings is the ones that are induced by maps that tell us for a given point x, we send all that mass to a unique point t of x. Okay, now the key examples to keep in mind for this optimal transport problem, I think two are only two I'll really refer to a bit in this talk. One is Munge's cost, so the one that kind of first appeared when this problem was introduced a few hundred years ago, was where this cost function is the distance. Okay, so the cost you pay for transporting mass from a point x to point y is directly proportional to the distance you're traveling. It takes work to transport, the literal physical mass. Now, this cost function turns out to be a bit degenerate, a bit tricky in the mathematical theory because the optimal coupling turns out to be non-unique typically. Now, why might this be non-unique? Well, the space of couplings is a convex set in the space of probability measures, and you're optimizing here a linear function of the probability distribution. So there's kind of no reason in general that a linear function optimized on a convex set would obtain a unique optimizer. But okay, in plenty of cases, this does work out. The quadratic cost is probably these days the most famous example in optimal transport that has a very rich structure. This leads to the Wasserstein distance W2 that I mentioned in connection with the gradient flow theory before. And it's a famous result of Brunier that in the quadratic cost case, well, because we're dealing with absolutely continuous marginals here, the unique optimal coupling is in fact supported on the graph of a function, which means the y coordinate is just some function of the x coordinate. So this is a nice structure that I'll refer back to a bit later on. Now, what is entropic optimal transport? Well, for computational purposes, the optimal transport problem can be rather difficult to solve, and I'll say a bit more about this computation dimension in a moment. But one thing you can do to ease the computation is to add a bit of a regularization to the optimization problem. Okay, so this previously was optimizing a linear function over a convex set. But now if we add epsilon times an entropy term, then we get a strictly convex function that we're optimizing over this convex set. So we get a unique optimizer as soon as epsilon is positive. And this relative entropy here, the usual choice is to make the reference measure mu times nu, the product of the two marginals. And when you do this, the optimal coupling for this regularized problem must have finite entropy, and therefore the optimal measure is actually diffuse, so it's non-atomic now and can no longer be supported on the graph of a function. So this regularizes things in several senses. It gives you a strictly convex problem. It gives you a diffuse optimizer rather than one that degenerates over this lower dimensional set given by the graph of the function. Now this entropic optimal transport problem really blew up in popularity a bit over a decade ago, thanks to this very influential paper of Marco Couturi, which showed that you really save a lot of computation time in this entropic optimal transport problem compared to the original one, because there's a way to adapt this famous algorithm due to Sinkhorn in matrix analysis to use it to solve this entropic optimal transport problem. So this has really been the driving force behind the applied and computational side of this entropic optimal transport problem, and I think it's used in statistics as well. So this is optimal transport and its entropic version are really used in a lot of kind of modern data science applications in terms of aligning data sets and transfer learning and some other statistical and ML topics that I don't want to talk about in too much detail. I do want to mention a couple of other kind of places this entropic optimal transport problem came from. One being this old thought experiment of Schrodinger, sometimes called the lazy gas experiment, where you imagine that you're given that these marginals mu and nu represent observations you're making, observations of a point cloud at time 0 and a point cloud at time 1. So you observe a bunch of particles at time 0, and you know that these are Brownian particles. So as soon as you run the clock, they'll kind of diffuse according to Brownian motion. But after time 0, you close your eyes and you open them again at time 1 to see some new configuration of particles. And you want to know what's the most likely path that happened in between. Now, keep in mind, you don't have names attached to these particles. You just see the distribution, but you don't know which particle at time 1 came from which particle at time 0. So the question is kind of how did the Brownian dynamics interpolate between these 2 point clouds? And if you do a large deviation calculation using Sanoff's theorem, you can actually end up with a variational problem to describe the most likely path that takes exactly this form with the quadratic cost function. So this is the way this Schrodinger lazy gas problem has been mathematically formalized as of a few decades ago, and this has been the subject of a good deal of research since then. One other place I'll mention that this entropic optimal transport problem comes up is just in the mathematical context, where it turns out even to prove things about a standard optimal transport problem, it can be useful to add this epsilon and then send epsilon to limit to 0 at the end of the day. So this entropic regularization has been a useful intermediate tool for some new kind of proofs of optimal transport facts, like Caffarelli's contraction theorem and some other things. So there are kind of 3 main areas I'll stress that this entropic optimal transport has gotten a lot of attention. Probably the big one these days is in this computational and statistical context in a variety of ML topics, but another one is this Schrodinger lazy gas, and the third is just it's kind of a useful mathematical tool, it turns out. So this is just to motivate this problem that I want to focus on for the next few slides here. To say a bit more about the structure of this optimization problem, you can write down a kind of semi-explicit form for the entropic optimal coupling. And it turns out to admit this kind of interesting description here. So I've written here the form of the density of the optimal coupling. And what you do is you take the product of the marginals times e to the minus 1 over the cost function. Sorry, e to the minus 1 over epsilon times the cost function. And if you stopped there, if you didn't have these red terms, that would be exactly the kind of solution to the unconstrained problem, where you don't have to restrict yourself to couplings, but you can choose any probability measure at all. Now, if you constrain yourself to couplings, then the optimizer takes this form. You get these 2 new terms, this phi of x plus psi of y, that kind of play the role of Lagrange multipliers for the marginal constraint. And the key point here is that this is an additively separable function of x and y. So the x and y are separated by a plus sign. Okay, and this very nice characterization of the optimizer is that if you find any coupling of the given marginals whose density can be written in this form for some functions phi and psi, then this is your unique optimal coupling, actually. And these phi and psi are uniquely determined up to an additive constant because you can add something to phi and subtract it from psi without changing anything. So these kinds of mysterious functions are called the Schrodinger potentials, and they're really the protagonists in a lot of analysis of this entropical optimal transport problem. They have some kind of nice structure. If you use the marginal constraint and then kind of differentiate things, you can express the gradients of these potentials as conditional expectations. And this kind of connection initially sort of inspired the stochastic process I'll introduce in another slide or two. So if you take the gradient of this first potential, you get the conditional expectation of the gradient of your cost given the x variable. So these are kinds of remarkable identities that have inspired the use of these gradients of potentials as kinds of substitutes for your optimal transport map itself from the unregularized problem. So there's a really rich structure for this entropic problem to exploit, which is in part why it's become so popular. So this is the optimization problem, and to come back to the main thread of the story here, I want to introduce a stochastic process that kind of plays the role for this optimization problem that Langevin dynamics played for the unconstrained optimization problem at the beginning. Question about strictly convex versus strongly convex regularizers, the latter being very common in Euclidean optimization settings. Yeah, good question. So I guess I don't have much to say about this distinction. Really, I'm using just strict convexity here so far to say that we have a unique optimizer. But yeah, I guess in some contexts, it's better to know something about strong convexity, which in this Wasserstein geometry setting, you could have if these marginals were strongly log concave, which is an assumption I use a bit later on for one quantitative theorem. So there does seem to be sort of a similar role for strong convexity versus strict convexity here. So, okay, if I want to try to introduce now a Markov process, some dynamics to sample from this probability measure, which I'll just repeat the structure here on the next slide. There's a kind of bad idea and a good idea. Before I do this, let me actually just say one more thing about what this entropic optimal transport does here, and I've borrowed this image from this book of Perret and Couturi, just to give you a bit more feel for what this is doing. If you have these two marginal distributions, I should have used mu and nu here, then the optimal transport map from mu to nu actually looks like this kind of curve over here. Okay, but if you take epsilon decreasing from left to right, this picture just sort of shows what the typical entropic optimal transport coupling looks like. So here is large epsilon on the left and small epsilon on the right. And for large epsilon, you get a very kind of blurry, very diffuse picture because the entropy term is dominating, and you want pi to be close to this product of the two marginals. So you're kind of close to just the independent coupling here on the left. And as epsilon gets small, this entropy term goes away, and you're really just solving the original optimal transport problem. So this is kind of what's happening here in this picture to give you a feel for what this is doing. Another question in the chat here, are there any other common regularizers considered for optimal transport? Yes, actually a very popular one that's been getting a lot of nice theoretical study recently is to use the chi-squared divergence in place of relative entropy, which gives you a kind of different structure for the optimizers and tends to enforce more sparseness. So you'll have kind of a less blurry picture in the middle here and something with really a bounded support kind of around the true optimal coupling. So chi-squared divergence is the main other example that I've seen studied quite a bit. This would be called quadratically regularized optimal transport. Okay, so let me return to the problem here at hand, which is how would we generate samples from the optimizer of this entropic optimal transport problem? Okay, and one idea that kind of might jump out at you is to take this formula we had for the density of the optimal coupling and just try to write down what the Langevin dynamics would be associated with it. Okay, and when you do this, you get a reasonable looking pair of SDEs, since we're dealing with X and Y coordinates now, okay, if you didn't have these red terms, you would just have Langevin dynamics for the optimization problem, which does not have any marginal constraints. But if you put in these gradients of the potentials, sure enough, this is just Langevin dynamics for this probability density, and this will converge as time goes to infinity to this invariance measure. But this is kind of useless because, from a sampling perspective, because this would require you to know ahead of time the potentials phi and psi, which are kind of part of the solution, part of the pi star that you're trying to identify. So this doesn't really take you anywhere, but kind of inspired by the conditional expectation representation from a couple of slides ago, if you think about it for a bit, you can kind of guess an alternative dynamics, or you can derive it directly from gradient flow principles, although I won't describe that in any detail. At the end of the day, the dynamics that you end up with that we studied here, and we call these the projected Langevin dynamics, again, if you ignore the red terms, this is Langevin dynamics for the problem without any marginal constraints. We get these funny looking red terms here appearing in the true dynamics we're studying that play an interesting role of enforcing the marginal constraints in these dynamics. So this will be the subject of the kind of first main theorem in a bunch of the talk here. What's going on with this funky looking new stochastic differential equation? So I want to stress before I say anything more about these dynamics that this is a very unusual stochastic differential equation because of these conditional expectation terms. So this conditional expectation, I need to be clear, is taken with respect to the joint distribution of the solution process xt, yt itself. So in some sense, the drift of this SDE depends on the conditional densities of one coordinate given another. So this kind of fits into the realm of what's called Mikine-Vlasov equations, which are SDEs in which the dynamics depend on the distribution of the solution, but a dependence on a conditional distribution is quite unusual and kind of falls outside of the scope of most of the theory of Mikine-Vlasov or mean field dynamics. So for this reason, we actually had to kind of start from scratch in terms of even just proving existence and uniqueness for this SDE. So that's not the part I want to focus on, but that took a significant amount of work, and that's kind of part one of the main theorem here. But the main messages are in parts 2 and 3 of the theorem. So let me walk you through the theorem statement here. The assumptions are reasonably mild. These, so I'll remind you, the marginals, the u and v functions come up as the potentials, let's say, of the marginals. So those show up here. The cost function and these two functions u and v, I just assume are twice continuously differentiable with bounded second derivatives, but the functions themselves and their first derivatives do not have to be bounded. And we basically wanted to cover sort of the benchmark example of quadratic cost function and Gaussian marginals. But more generally, we take any functions u, v, and c with this form, and the marginal densities mu and nu should be sub-Gaussian. Then the first main theorem of our work says that if you take any initial distribution P0, which is a coupling of the correct marginals, then first of all, well, we can really genuinely solve this SDE. This has a unique solution from this initial position, this initial distribution. The second part of the theorem is an interesting one already. It says that actually at every time t in the future, we stay within the space of couplings. So at every time t, we're still coupling the same two marginals. Even though these particles are moving around and the joint distribution is changing, the marginals are staying fixed over time. And so this is related to the fact that this is essentially a gradient flow within the space couplings in this submanifold geometry, but I'm not going to go through the details of that again. It's not entirely true. We only have a literal gradient flow when the marginals are one-dimensional. There's a slight gap in the higher dimensional case that I can touch on later if you're curious. But this is kind of the gradient flow idea. Oops. This is kind of the gradient flow idea in the second point here. The last part of the theorem is that as time marches on, we indeed converge to the optimal, entropically optimal coupling that we were after. So this theorem tells us that basically this SDE system kind of forms a natural candidate, say an analog of Langevin dynamics, but for the problem of sampling from this entropic optimal coupling. So I want to kind of explain a bit more of how this works and get a bit of intuition for these dynamics. First of all, I should say a bit about the sampling perspective here. If you want to actually implement something like this for computing your pi star or sampling from it, as with the Langevin SDE, you would need to discretize time somehow in this equation. But not only would you need to discretize time, you need to figure out how to approximate these conditional expectation terms. And this is a really tricky task. The natural way to do this is inspired from this McKean-Vlasov, this mean field connection. For distribution-dependent SDEs, the natural way to simulate things is through a particle approximation, where you duplicate the particles, you replace xy with x1, y1 through xn, yn, and replace these conditional expectations with some kind of estimator based on those particles. So one way I've done this with some undergraduates I have recruited for a nice semester project was to kind of help me implement and tweak this algorithm here. You duplicate again to n particles, and then for the conditional expectation term, you use like a Nadaraya-Watson, like a non-parametric estimator of the conditional expectation. And so written out, it is this sort of clunky expression, but we pick some kernel that has some bandwidth associated with it so that we can smooth out the sort of density dependence in the conditional expectation term. So once you do the smoothing, okay, you have quite a lot of parameters to wiggle around now. You have the epsilon regularizer still floating around, but you also have this bandwidth parameter and the number of particles that you get to tune if you're implementing this algorithm. And we don't have any theory about this yet, but simulating it does seem to work pretty well. So I've got a video here I'll show you of a simulation where we've taken one-dimensional marginals. One of the marginals is a standard Gaussian. One of the marginals is like a double well potential kind of thing. The blue line in the middle, the blue curve, is exactly the true optimal transport from the Gaussian to the double well. And we're taking the regularizer epsilon to be very small in this simulation so that we would expect to support the theory that the particles should all kind of cluster around this curve as time goes on, because the pi star, the entropic optimal coupling, should be concentrated around this actual optimal transport. And sure enough, as we simulate this, we see that the particles, I hope the video is working over Zoom, we do indeed see that the particles are kind of clustering very nicely around this optimal transport curve. So we initialize the particles from the correct marginals, but independently from each other. So we start from the independent coupling, and as time marches on, sure enough, we're convergent to the something that looks like the true optimal coupling. There's a question in the chat about how well we can approximate the conditional expectations. So how to choose, especially as a function of x and y. Yeah, so there's definitely quite a few questions here about the simulation that I'm sort of brushing under the rug and really don't have good answers to yet. So for one is the sort of standard statistical question of, how do you choose optimally the bandwidth parameter as a function of the number of particles? But, it's also not obvious what kernel you would want to use, or maybe if some other methods of kind of regression would be better suited to this kind of simulation problem. And a new comment comes into the chat, gets right at the next point I was about to make, that these non-parametric estimators and kernel density estimators, definitely are well known to suffer from the curse of dimensionality, especially if you can't go to higher order kernels, which we don't really know how to do here. So, it does seem like this method of simulation is going to suffer poorly for high dimensional marginals, kind of the form like n to the minus d plus something, plus 2 maybe is the non-parametric minimax bound here. So we wouldn't expect to do better than that in this kind of context, which does make me wonder if there's something better to be done. I have a talented PhD student working on the convergence analysis for this SDE system right now. And the results are too preliminary to be going into too much detail on, but stay tuned for some more work on this in the future. One thing I should be very upfront about is I'm really not yet claiming to have an algorithm that's competitive with the gold standard of Sinkhorn's algorithm, which is really the gold standard for numerically solving an entropic optimal transport problem. I would be very curious to understand if maybe there are some regimes where this kind of sampling Langevin type approach is advantageous to Sinkhorn, but it's way too early to say, and I'm against tough competition because Sinkhorn is very, very good. So this is, I guess, the last I wanted to say about really the applied direction that's still very much in its infancy for what we might do for sampling with this continuous time process that I've introduced. But nonetheless, I find this continuous time process to be very fascinating in its own right. And in the last few minutes, I want to elaborate a bit on the structure of these dynamics and some interesting features of them. So I want to focus specifically on the case of quadratic cost, where the dynamics take a somewhat simpler form, where the drift of x has y minus its conditional expectation appearing, and vice versa for the drift of the y particle. And we do have a second theorem here in the paper that's a quantitative convergence theorem. So this is much less general in scope and kind of limited so far in the sense that, so we can generalize this condition, as I mentioned at the bottom, but for the sake of simplicity, I've given here the case of strongly log concave marginals. And in this case, we are able to get a quantitative rate of convergence of the distribution PT of this XY pair toward its limit, the entropic optimal transport, as measured in relative entropy. And we get an exponential convergence rate. The exponent R sub epsilon is explicit, but kind of complicated, so I haven't put it in the slides here. The key limitation of this theorem is that it currently only covers the case where the regularization parameter is sufficiently large relative to certain aspects of the marginals. So in particular, the strong log concavity parameter shows up here and kind of keeps us from going all the way down to epsilon going to 0, which is what you would want to do if you're solving the unregularized optimal transport. And I don't know if this is something fundamental. It sort of mirrors the current known convergence rates for Sinkhorn's algorithm as well, which have a critical epsilon. But I don't know if this is kind of a real restriction or just an artifact of our proof technique here. So this is one of the many mysteries to me about these dynamics, kind of what's going on below this critical epsilon. Do we still, is there some difference convergence rate or what's going on there? Again, the first theorem tells us that qualitatively, this PT is indeed converging to pi star, but I just have no idea how fast when we get below this critical epsilon. So this is one of the many mysteries. Let me comment also to really go back to this analogy with Langevin dynamics. Something interesting shows up when we look at the zero noise version of this equation, which we didn't prove anything about, actually. All of our theorems are about epsilon strictly positive. But you could imagine, just setting epsilon to 0 to try to understand what's going on. This should be kind of what we get in the limit when we send epsilon to 0. And if you take epsilon to 0, you're left with a very strange but simple looking pair of dynamics here where there's no noise anymore. And if you look at this for a while, you come up with a whole infinity actually of different stationary joint distributions for this evolution. So I've said it in jargon here. All bijective Monge couplings are stationary. Well, what does this mean? If I take x0 and y0 with the correct initial marginals, mu and nu, and I take y0 to be some function of x, some bijective function of x, and vice versa, x0 is f inverse of y0, and we just take constant over time, xt and yt. Well, if yt is measurable with respect to xt, then this whole drift vanishes because the conditional expectation of y given x is just y itself. And vice versa, if x is measurable with respect to yt, this drift of the second equation vanishes. So in this case where if you take x and y to be any measurable functions of each other with the correct marginals, this equation won't move. X and y will just stay put. But there are many, many different ways to couple two marginals with bijections, right? If you have two standard Gaussians as your marginal, you could take y to be plus or minus x, for instance. Either way will be stationary, but only one of them is the actual optimal transport coupling. And there are actually infinitely many ways to couple two non-atomic distributions in this way. So we have, in the zero noise case, we have this whole kind of infinite dimensional, this infinite set of unstable critical points, let's say, for these dynamics, which is somehow much worse than the case in Langevin dynamics, where if the function f was non-convex for Langevin dynamics, you have these bad critical points corresponding to local minima, or maybe these unstable ones like the top of a hill here. But as soon as you add any amount of epsilon positive, you restore uniqueness and a unique limiting distribution. At least in the Langevin case, if you have a convex potential, then everything is very nicely behaved for the zero noise equation as well. In this case, in this optimal transport context, no matter how nice our marginals are, it seems, the zero noise equation is very nasty for us because it has infinitely many bad stationary points that don't correspond to the optimizer. So this is sort of an interesting point, and I think this kind of zero noise story shows pretty well the analogy with standard Langevin, that any amount of positive noise kind of gives us back this unique ergodic behavior for this process in some sense. Time flies. I'm at 12:30 already. I guess maybe I should wrap up in the next minute or two. Is that right? I don't think I remember exactly what time he told me I should aim to stop by.
Yes, there are 2 to 3 more minutes.
Okay, great. Yeah, so I think this is correct in the question here that there should be a trade-off in the size of the time discretization parameter and the regularization. Exactly. You could kind of get into weird kind of overshooting behaviors, but this is something we haven't really investigated theoretically in that much depth yet. We're still working on the particle approximation and haven't even turned to the time discretization analysis yet. So let's see, in the last 2 minutes, let me just conclude by maybe mentioning a very concrete example, which is the Gaussian case. When you're dealing with any new kind of stochastic differential equation, if the coefficients are linear, you should probably have a Gaussian solution. And indeed, that's what happens here. You can make an ansatz. So here I've looked at the case of one-dimensional standard Gaussian marginals for simplicity. And what happens is if you kind of make the guess that at every time t, your joint distribution, your solution of this process is Gaussian, joint Gaussian with covariance CT, which better live between -1 and 1. Then, okay, joint Gaussians have very explicit conditional expectation formulas, which become linear in the conditioning variable. So you plug that back into the SDE here, and you get now a linear SDE with some time-dependent parameters. You solve it explicitly, and then compute the covariance to check that your ansatz was correct. And when you do this, you end up with this Riccati ordinary differential equation that your covariance parameter needs to satisfy. Riccati because there's a c squared term on the right-hand side. And if you plot a phase diagram of this ODE, so this right-hand side, this is kind of the right-hand side as a function of c, is this negative quadratic that has a unique 0 between -1 and 1. And so that's where your c will converge as time goes to infinity. If you start to the left of it, say over here, then you'll kind of go to the right because your derivative's positive. If you start to the left, you move toward it, and all is well and good. But when epsilon goes to 0, this parabola shifts over until it right at epsilon equals 0, we pick up another 0 within this allowable interval of -1 to 1. We pick up a second critical point, basically, where c is equal to -1. The covariance is -1. So then if you start right at exactly that point, you don't move, you're stationary. If you start anywhere else, you indeed move to the correct kind of optimal one, all the way on the right here, where c equals 1. And this corresponds exactly when you're thinking about coupling two standard Gaussians. This kind of correct optimal coupling is just to take y equals x to optimally couple two Gaussians, two standard Gaussians. This one on the left, this kind of bad equilibrium point corresponds to y equals -x, kind of fitting in with the discussion on the previous slide. So hopefully this is a kind of more concrete example to think about. I've run out of time to talk about connections with functional inequalities like log Sobolev and aspects of the proofs, and even the mean field variational inference story, which has a nice kind of geometric picture behind it. But you can browse that on the slides and in the paper if you're curious. So this is a good place to stop. Let me thank you for your attention, and I'm happy to take any further questions.
Thank you so much, Daniel, for the interesting talk. So for the sake of time, maybe let's take 1 to 2 more questions, if there are any from the audience. Okay, great. So there seems not to be any lingering questions. So maybe let's give Daniel another round of applause. And then thank you so much again for accepting our invitation. So Daniel would actually conclude the SNAPP seminar series for the fall quarter. And so thank you everyone for attending, and please stay tuned for our announcements for future SNAPP seminars in the upcoming quarters.
Thank you all, and thanks for the questions throughout. Appreciate it. Have a good holiday, everybody.
Thank you.